Alright, here's section 7.2, example 2. Write the following sums using summation notation. So we just barely went through example 1, where we had these problems given to us in summation notation. And we took those and broke them down into the individual terms, and then took those terms and added them together to get the sums, right? So in this case, we found the first. Well, we found 5 terms for this one because we started at 2. So each one added an additional 3. So there's kind of a, oh, I see what those dots were. So this was like a dot, dot, dot. Add 3, you get 7. Add 3, you get 10. Add 3, you get 13. So you've got the second, third, fourth, fifth, and sixth term, adding together to get 35. This one, when I did this in class, I changed it to a decimal right off the bat. This one shows changing it to a common denominator of 100 to the 4th power, and then combining all those together into a fraction answer instead. But the decimal answer is fine in my opinion, so you've got the first 4 terms. This was the complicated one where we actually wrote it all out. We left x in there, so you can see how I started writing this out when I wrote this up last year. The completed version of this was on our previous video. Kind of ugly, but gave us a general idea of the process. It also included 5 terms, just like our first one, because it included 0. So 0, 1, 2, 3, and 4. Okay, now let's go the other direction and write some summations for these sequences. This first one is finite. Let's figure out what's adding each time. So looks like we're adding 3 again. So I feel like that's enough for us to figure out that this is arithmetic, not geometric. And we're adding 3. So let's go ahead and write a little equation for this. So a general or an explicit formula. Alright, so our explicit formula would be 3 times n plus whatever number we need to start it at -5. So that would be like a -8. I'm actually going to show this process a different way using the formula that we learned in section 7.1. So that formula says, and the one that's on your formula sheet, so a sub n is equal to a sub 1 plus n minus 1 times d. So a sub 1 is -5, and d is 3, because it's going up by 3 each time. So that's a -5 plus 3n minus 3. Combine our -3 and our -5 together, and we get that -8 that we figured out just by thinking through it. So there is a formula for that. I've just been doing the little think through way of finding that number. Basically the y-intercept, but we don't have a 0 term, so we don't have that written down. But we have to add 3 to that to start in our first term. So just another way of finding that value. Okay, I'm going to kind of just grab this and put it off to the side out of the way for us. Alright, so our goal here is to write our summation notation. We don't actually have to find the sum, we just need the summation notation. So I'm assuming this is our first term, right? So we're going to go from n equals 1 to, do we put a 22 here? No, we don't. 22 is not the term number. This is the term number of the last term. This is the actual term of the sequence. We need to know what term number that 22 is. So we're not quite done yet. We do know that the formula that goes in here is a 3n minus 8. So we got to do one more thing. We're actually going to use this formula and find n by setting it equal to 22. Because a sub n is 22, and that will give us the value of n, which is the last number in our sequence for this series. Alright, so then we can just add the 8 to both sides. So 3n would equal 30, and that means n would equal 10. So we just found that. That would be the 10th number. So a 10 goes there. The 10th number is the last number, not the 22. These numbers are not the actual numbers in the sequence. These are the term numbers, right? And you get the actual numbers in the sequence by plugging these term numbers into the sequence. Hopefully that makes sense. So this is my finished answer, because all I'm doing is writing out the summation notation. Let's look at the next one. So the next one has 5, -5 halves, +5 fourths, -5 eighths. It looks to me like we're multiplying by a -1/2 each time. Doesn't that look right? So that's geometric. So the formula for geometric is that easy to write one where we do our a sub 1. I'll just make a little note of it. So we have a sub 1, so a sub n equals a sub 1 times r to the n-1 power. On your formula sheet, they don't put a parenthesis around it. It's just when you're writing actual numbers in there, you probably want to put the parentheses in to distinguish between the first term and the base of the exponential. Okay, so the beginning term is 5. The r value is what we multiply to get each next number. It looks to me like it would be a -1/2. If you're unsure of what that number is with just looking at it, you can always do the little thing I think I showed you earlier, where you can take term number 2 and divide by term number 1, or you can take any term and divide by the term before it. So then we're dividing fractions, so we're going to want to copy dot flip, and that gives us, the 5's cancel out, so -1/2. So there it is, that's r, right? So can't do it in your head, you can always do the division for that ratio. I left this in the middle. I have to have an exponent of n-1, and then this is going to go from n equals 1 from our first term to ... infinity. So that's where we end. That's our sigma or summation notation for this problem. We're not actually finding the sum yet. Alright, the next one is actually the same geometric sequence. It just has an ending point. So we start at 1, and this time we're going to end at some number. We need to figure out what number that is. It's going to be the same formula here, because it's the same sequence. We just have to have that ending number. So let's go ahead and figure out what's going to work. We can kind of just figure it out by figuring out what we would need to multiply, how many times we would need to multiply 1/2 together to get 1024. So if you want to play around with that a little bit, you should discover, so here's my little side note, that 2 to the 10th power is 1024. And of course an even power is going to be positive. Even, well, yeah, so this would be a negative power to get a negative number there, positive power, negative power. But that negative power is obtained by taking in a number and subtracting 1 from it. So the actual n value is going to have to be odd, because we're subtracting 1 from it. So this needs to be a 10 after we've subtracted 1. That means that n needs to be 11, because we would need to be able to take 11, subtract 1, and then do our -1/2 to the 10th power to get our positive 1024. And then this 5 at the beginning is what's going to ensure we have that 5 on the top of each one each time. So that completed this, but I really want to show this problem with using a logarithm to solve it instead. So this is 11, but let's work through this using a logarithm instead of just kind of our guess and check. So I'm going to say that 5 to the -1, times -1/2 to the n-1 power needs to equal 5 over 1024. We need to solve for n. So we're going to start by dividing both sides by 5. Divide by 5, that's going to cancel out our 5's. So now we just have -1/2 to the n minus 1 power equals 1 over 10 to the 24. So now we're going to use a logarithm. Oh, there's a stray number down there. I don't know where that came from. Something I didn't erase earlier. Okay, so now let's do the log of each side. So I'm going to do the log of this and the log of that, and then I'm going to pull this forward, so I'll have n minus 1 times the log of negative 1/2 equals the log of 1 over 10^24. So then this would distribute, I'm really running out of room here. So this would be n log negative 1/2 minus 1 log negative 1/2. Oh, what is wrong with this picture? You can't do the log of a negative 1/2. We'll scratch that. We're not going to be able to do this particular method to solve the logarithm because it's impossible to do the log of a negative 1/2. I love it how I start going on what my brain thinks I should do instead of looking at my paper and figuring out that I should do it some other way first. But hopefully that shows you, yeah, we make mistakes. We just go back and try again. Okay, so instead of doing this that way with a log of each side, why don't we just use a log with a base of negative 1/2? Yes, now I'm consulting my scratch paper in case you wondered. Because I've done this problem a few times now and I'm still continuing to get the wrong answer. Can I have a logarithmic base that's negative? I think I can. So I should be able to change this to log form. So instead of this to this power equals this, it would be the log base negative 1/2 of 1 over 10^24, right? That equals our exponent because a logarithm equals an exponent. So then you should be able to do this logarithm with a base of negative 1/2. So just think to yourself, negative 1/2 to what power is 10^24? So we're just trying to figure that out, right? So we figured that out already that it's, well, it's 1 over. So 2 to what power is 10^24? And it doesn't matter that it's negative because as long as it's an even exponent, it'll be a positive value. So we should end up getting negative 1/2 to the 10th power is 1 over 10^24, correct? So that means that this thing equals 10. This whole thing right here equals 10. Which equals n minus 1. So then to find n, we add the 1. We have n equals 11, and that is the number that goes on our summation notation and gives us our final answer. Those of you that were in class saw me do that a different, well, think through it and get a wrong answer earlier. So now I've gone through it another way where I got stuck at some point. I think we've got that now, but this video ended up being a lot longer than I expected it to be.